In this video, we'll use the ADALM2000 to measure the gain bandwidth product and slew rate of some op-amps. We can use these measurements to compare op-amps purchased from Amazon with op-amps purchased from normal electronics suppliers. Are the op-amps from Amazon the same? The test procedure is quite simple. We put the op-amp into an inverting amplifier configuration where the gain is minus R1 divided by R2. We then put in a low frequency input signal and note the amplitude of the output. And then we increase the frequency of the input signal until the amplitude of the output is reduced by 3 decibels. That second frequency, the higher frequency, is then the bandwidth, which we multiply by the gain to get the gain bandwidth product. For many op-amps, the gain bandwidth product is roughly constant, so you get the same number regardless of the gain that you configure in the inverting op-amp. But we can test with multiple values of R1 and thus multiple gains in order to determine if this is really the case for a particular op-amp. The other thing that we have to watch out for is the slew rate of the op-amp, and that's the maximum rate at which the output signal can change from coming from the op-amp. And if the test requires that that slew rate be higher than the op-amp can do, then the test will be invalid. So it's important to look at the shape of the output waveform, especially at the higher frequencies, and make sure that it still looks like a sine wave. The slew rate that a test imposes is proportional to the amplitude of the input signal, so the easiest way to avoid slew rate problems is to use a lower amplitude on the input signal. We can do this in an LT SPICE simulation using an AC analysis. That produces a Bode plot just like we can with the network analyzer on the M2K. So here's an example of the SPICE output, and you can see the cursors were used to find the point where the output signal is 3 decibels down, and then that gives us the bandwidth that we can multiply by the gain to get a gain bandwidth product, in this case of about 8.8 megahertz. But be aware that this is using an NE5532 SPICE model that I just got off the internet. I don't know how accurate it is. The M2K connections are also straightforward. W1 and 1 plus connect to the circuit input, 2 plus connects to the circuit output, and 1 minus, 2 minus, and ground connect to the circuit ground. I have several op-amps to test. 2 of them come from this kit that I bought from Amazon. And oddly, given what I'm about to say, I recommend this kit. It's a good source of some components to just play around with, and the price is very good, and the components do function. But I am very sure that the NE5532 in this kit is not actually an NE5532, and one way you can tell is to just get out your digital multimeter and put it in diode test mode and test across the positive and negative inputs of the op-amps. In a genuine 5532, you should see a diode drop in both directions. And on the op-amp in this kit, I don't see that. So I'm interested in comparing its performance to that of an NE5532 that I bought from Mouser.com. I also have a TLE2082 op-amp that I'm interested in testing. This is a more expensive op-amp. It's not exactly a so-called jelly bean component, and it'll be interesting to see its performance in comparison to the others. Here's the breadboard and also a zoomed in view of it. It's pretty simple. You can see I'm running at plus and minus 12 volts. So let's go through the test procedure. We have a 5532 from the Bojack kit installed, and R1 is about 47K. So we're in a situation where we expect a gain of about minus 10. To start with, let's confirm that the circuit is working as we expect. So we want to start with a sine wave at 200 millivolts peak to peak amplitude. This is to avoid issues with slew rate that we'll talk about in more detail later. And our frequency is very low. We want to start with a frequency that doesn't challenge the op-amp at all. Probably you could use 100 hertz instead of 20. 20 might be lower than is really necessary, but we've got 20. So that's what the signal generator is set to do on its first channel. The second channel is disabled. So now if we go to the oscilloscope, we can, well, let's just start the signal generator and start the oscilloscope. And we can see our signal now. It's been adjusted. I'll show you the channel 1 settings briefly and the channel 2 settings briefly. We're also using the statistics method for measurement. So I'll bring up the measurement panel here. And So we're measuring the peak to peak of the input and the peak to peak amplitude of the output. And you can see that one is about 10 times the other, which is what we expect for our R1 value. But let's reset and make sure we have accurate values. And we should note these values down. Um, I'll have a table later that summarizes results from lots of runs, but we want to make sure that these are all reasonable looking things. And so we're going to use the network analyzer to find the bandwidth frequency, and that would be the frequency at which the output amplitude is reduced by 3 dB, which means it should be this voltage multiplied by approximately 0.7. So let's go ahead and do that. So we'll stop the signal generator and we'll stop the oscilloscope, and we'll go to the network analyzer and take a look at its settings. And so we need our amplitude to be 200 millivolts, I think we wanted. That's peak to peak. And we have to somewhat guess at the range. Linear is good for the sweep, but we were starting at 20 hertz, and we have to kind of guess the how far we need to go to catch the 3 dB down point, and this is probably okay at 340 kilohertz for this. You might have to experiment with that a little bit. The magnitudes are also worth adjusting, but let's just start it and see if we see it. And if not, we'll do something to make a change. Okay, it started. And so now you can see the output starting to accumulate from low frequencies to high. And as time goes by, we should start to see the output amplitude reduce. And we're eventually going to use the cursors to measure the frequency at which the output is down by 3 dB. So this will just take a little while. The sweep is nearing completion, and we can see that the amplitude has gone down a bit from where it started at a very low frequency. So we have to enable the cursors, I guess they're already enabled, to find the 3 dB point. And one thing that's helpful with the cursors is to have the position down here so we can see them. And I guess that's all. And so now let's get the first cursor positioned to where the amplitude's kind of at a maximum near the beginning. The exact point doesn't matter all that much. And then we move the second cursor back and forth, looking for delta magnitude right around here to be 3 decibels. That's actually 3 decibels down. It doesn't really matter whether you do it minus or negative. So how close can I get? 3.02. There's a little bit of noise in the signal, so it's sometimes a little ambiguous where you go, but that looks pretty good. And so what do we see for our output frequency? It looks like it is 278.8 kilohertz. Let's just call that 279 kilohertz, since it's certainly within our margin for error. And so that's the bandwidth at this time, and the gain was a little over 10. So the gain bandwidth product would be um, you know 10 times 279 kilohertz roughly. But we need to check that this is correct. And so let's dial in 279 kilohertz to the signal generator. So we were at 20 hertz. Let's go to, what did I say? I already forgot. Network analyzer, 279 kilohertz. So change the frequency to kilohertz, 279, 279. All right, took it that time. And we can go back to the oscilloscope, start the signal generator again. And now we're going to have to adjust to be able to see this much faster waveform. The Scopy shows nothing if okay, what's going on here? Oh, the oscilloscope isn't running. Okay, that's good. And so now we see the waveform pretty well. And we might even be able to zoom in on the output waveform a little bit, like so. And so one thing that's important at this point is to make sure that that output waveform, the purple one, looks like a sine wave. If it's starting to look like a triangle wave, then the system is slew rate limited, and you'd have to decrease the input amplitude a little bit. But this looks okay. And so the kind of to check the results of the network analyzer, we want to see that this amplitude is is where we expect it to be. It should be lower. Let's actually go to the here and always reset the statistics. And so we can see that our input amplitude hasn't changed much. That's good. It's still around 200 millivolts peak to peak. But now our peak to our output amplitude is 1.423. And so if we multiply 1.423 and actually divide that by zero point 0.7, we get to around 2. So that's approximately correct. We'll take a look at a table of results in more detail, but that's the basic approach. You start by verifying that the system's working with a low frequency waveform. Kind of note that the gain is what you expect it to be. It should be near the theoretical gain. And then you can use the network analyzer to find the frequency at which point the output amplitude is 3 dB down, and then that frequency becomes your bandwidth, and multiply that by the gain to get the gain bandwidth product. I've done lots of runs with 4 different op amps: the NE5532 from the kit, the NE5532 that I bought from Mouser, and also a JRC 4558D from the same kit as this NE5532, and finally a TLE 2082 CP that I bought from Mouser. That's a more expensive, higher performance op amp. So the test that we just did was equivalent to this row here, with this 5532, a 47K R1. And I think on that run we just did, we saw 279 kilohertz as the bandwidth, the point at which we were 3 dB down. So on this one I got 280. There's a little bit of variation from run to run. And so the gain bandwidth product is then 2.85 megahertz. And that's what we get there. And then so I also recorded the the theoretical gain, and the gain that we actually saw at low frequency, and the voltage of the input signal, and the amplitude of the output signal at low frequency, and then the voltage of the input, which should be the same about at high frequency, and the voltage of the output at high frequency, which should be about 70%-ish, 71%-ish of the input. And so this column shows the amplitude being about what's expected. And you can see there's a little bit of variation there, but basically the procedure works pretty well. You can just see that there's a little bit of error involved. And so what can we conclude from this? So first of all, this particular NE5532 has reasonably constant gain bandwidth product, regardless of the gain. And that's common for lots of different op amps. And so that's as we expect. But how does it compare with the NE5532 from Mouser? Well, it doesn't match at all. The first of all, the 5532 from Mouser doesn't show so much. Doesn't show a gain bandwidth product that's as much of a constant. And we'll look at its data sheet and get some confidence that that might be a reasonable result. But one thing to notice is that the gain bandwidth product of the Mouser NE5532 is much higher than the gain bandwidth product of the one from the kit. So at least in terms of this metric, the Mouser op amp is significantly outperforming the one from the kit. So if you're expecting the performance of an NE5532, you might not want to use the one from the kit. But it does work as an op amp. And so one thing that I find kind of remarkable coincidence, if we look at the performance of the JRC 4558 from the kit, the results are almost identical to this NE5532. See, 2.5 versus 2.48, 2.78, 2.76, 2.85, 2.83, 2.85, 2.81. And I guess I don't have any way to verify that, but I wonder if this NE5532 is actually just a remarked version of this op amp, and what it is exactly, I have no way of knowing. but you can see their performances are very similar, and it might be interesting to compare their slew rates as well and see if they're a lot alike. We'll do that coming up. And I guess the last one to look at is this TLE 2082 CP, and it is more normal in the sense that all of its gain bandwidth products are about the same, and you can see that they're pretty high. So it's consistent and pretty high. So this is a pretty fast trouble-free op amp actually. And just the only trouble is it costs 5 times as much as even a Mouser. I bought this from Mouser and this from Mouser, and the TLE is maybe 5 times as expensive. So let's take a look at whether we are too concerned by the gain bandwidth product not being constant for this op amp. Its datasheet shows frequency gain response in a somewhat unusual way. They have different graphs for different conditions of resistors in the circuit that they use to test this. And by the way, this is a logarithmic display, so these are mostly showing low frequencies, and then past a threshold, you see the more typical, reduction in amplitude with frequency. And notice that the slopes are different. So, maybe this is a somewhat unusual op amp. And also the circuit that they use to test is different than what we've been using in this video. This is a form of a non-inverting amplifier instead of inverting, with some other stuff added, including a load. So I guess the bottom line is I'm not sure what to think about the fact that the gain bandwidth product isn't particularly constant. I may have to look into that in a future video. I think for now, let's instead go and look at some slew rates. We have the Mouser 5532 in the circuit, and it's also with resistors to give a gain of around 10. And we have the signal generator set to produce 791 kilohertz sine wave with an amplitude of 200 volts peak to peak, 200 millivolts peak to peak, like we saw before. So if we look at the oscilloscope, we can see that the output looks sinusoidal, which we said was important for the test to be valid. But what happens if we go back to the signal generator and switch this to 1 volt peak to peak? So now the output is clearly distorted. It doesn't look sinusoidal. And kind of the key culprit here is that the output is being forced to rise faster than the input, and in fact faster than the op amp can handle. And you can see that this slope is higher than this slope, and both channels are at the same vertical volts per division, 500 volts per division. So in this case, the op amp is slew rate limited, and that's why the output doesn't look sinusoidal. So to measure this, we can switch to a square wave. I reconfigured off camera to save time. The signal generator is now generating a 1 volt peak to peak square wave at 10 kilohertz. And the oscilloscope is just showing the output. It's also triggering from the output signal. The input's turned off, so we don't need to look at it. And so we can see that we're seeing an output square wave, but the slew rate determines how fast the square wave can rise. So if we kind of zoom in here, we'll see that rise time is definitely finite. And I think it would be best to measure this with the cursor. So let's turn cursors on and configure them. It's best to have them set to track. And then all we have to do is position them into the linear part of the rise. And we can measure the slew rate of the op amp by taking the delta V and dividing it by the delta T. So I'll pause and do that math. And the result is about 6 volts per microsecond. This is a slew rate that is in line with what I would expect for a 5532. So now let's pause and input the op amp kit 5532 into the circuit and measure its rise time. And we're back, and you can see that the scope is still doing the same thing with this curve, but the shape looks pretty different. In fact, I can move the cursors farther apart, and so now we're seeing a different slew rate. And let's see, let's do just a single capture here to make the numbers stop jumping around. And so we have 5.512 delta volts divided by 3.568. And that's giving us a result of about 1.54 volts per microsecond, much slower than the Mouser 5532. Now let's pause and install the op-amp kit 4558 and see how it compares. So we're back after a Scopy crash. We're now in the same situation, only I've replaced the op-amp kit 5532 with the op-amp kit 4558. Remember, I was suspicious that those might actually be the same op-amp. So now I'll do a single capture again to make the numbers stop jumping around, and let's calculate the slew rate of this 4558. So we have 6.376 divided by 3.949, 1.6 volts per microsecond. Pretty close to the 1.5 that I got for the 5532. That's close enough to make me continue my suspicion that in this op-amp kit that the 5532 and the 4558 are actually the same op-amp, but I can't know for sure. Well, this has gotten pretty long. I think I'll stop the video here. I hope you enjoyed it and found it informative.